Now this is a titration question, and we're being asked to figure out the pH at the start of this titration. And we've got, obviously it's a base, we can see that from just the shape of the graph that we're coming from a basic pH range, but also obviously we're dealing with a base, and we need to know a little bit of information to start this. We need to know the concentration of the actual base itself, and we also need to know a Kb value. So if we know a Ka value or a pKa value, obviously we can work out Kb. Now, in doing this question, there's some information we're given. Now, in terms of the base itself, we've been told that the acid is 0.0107. Yeah, how much acid is there? Well, if we were to look at the actual graph, we can find that out. So, if you come down from here and read that correctly, you'll find that 35 mils of acid is required. So we know the volume of acid is 35 mils. So I'll just put that in there. We've got 35 mils, and we're told we've got 25 mils of base. So if we use the formula C1V1 equals C2V2, this is just the stoichiometry of this is there's just one proton being exchanged here, so we don't have to worry about that ratio too much there. We can just do this to work this out, and we'll go ahead and replace that with some numbers. So that'll be, for instance, 0.107 times by 0.035, and whatever that adds up to, divided by the volume of the base that we're interested in, we'll find we get this concentration here, 0.01498. Now, that obviously can round to three significant figures of 0.0150 moles per litre. So we've got one piece of information that's necessary. Now, we're not given Ka, and we're not given Kb. We do need to use Kb to do this calculation. So that means we can only calculate this in one way, and that's to use the graph. Now on the graph, 35 mils, remember, is equivalence point, so that means 17.5, which is in this region here, but we'd have to take care, it's about 15 there, 17. Now, if you come up here and go across, now I can't do this that accurately, but if you do this accurately and make sure, you've got to be very precise that you do this interpolation quite well, you'll find that you get a value of 9.5 if you do it properly. That's probably more there. But anyway, that's going to be your pKa equals 9.5. Now we just need to do a calculation to turn that into a Kb. Now this last part is just a straightforward calculation. We're going to put this, I've just transferred pKa into Ka and here, and you can actually do this calculation in a variety of ways, but we're going to also now then change that into Kb, and that should allow us to do the final calculation. So when we do that, we're going to have this number here is Kb, so that goes there. That's a concentration, so remember we're going to multiply those two together, take the square root, and that'll give us a hydroxide ion concentration, and that should end up with a pH of 10.84, but we can round that to being something like 10.8, okay, for 3SF. So I'm assuming you're confident with being able to multiply that, take the square root of it to work out the hydroxide ion concentration. Obviously once you've got that, you can convert that into a pH value, and that's the first question done, part 1. Now this next question, which is to show that the pH at equivalence point is 5.9, it's one of those kind of more straightforward questions in terms of you've been given the answer, you're told to work it out and show you're working. So obviously you're going to use Ka equals the hydrogen ion concentration squared over HA. Now obviously this is that simplified version of this formula where we assume that H3O plus is going to be equal to the A minus, or the concentration of the conjugate base, and we make some assumptions in doing that, but anyway, you already know what the Ka is. We need to work out concentration of the weak acid. Now remember, this started off as a base, and at equivalence point all of the weak base had effectively been converted into a weak acid, and if we can work out that concentration, because it has been diluted, initially we had 25 mils of weak base, so if that all turned into acid, we'd still have 25 mils, except we added 35 mils of HCl to do that. So the total volume is 60 mils. So 25 over 60 times by 0.015, which was the concentration of the base, gives us what the concentration of the conjugate acid would be after it's been diluted, which is 0.00625 moles per litre. Now if we put that into the calculation, we multiply that by Ka and take the square root, we'll get a concentration of, we'll get a pH of 1.41 approximately, times 10 to the negative 6, and that ends up being a pH of around 5.85. Depending on how you round, you may get it slightly different from that. And that's part 2 answered. Now, for part 3 here, we're asked to relate the change in pH and the shape of the titration curve to the change in the nature and concentration of the species in the flask as the titration is carried out. So this really can be broken down into really about 4 regions. What's happening right at the start, where you just effectively have a weak base present, so just a dissociation of the base in the water. And if you're talking about this, you need to talk about the different species, so writing an equation would be a good idea to show what's happening. And then as you start to add the acid, what actually happens there, and as you go through the buffer region, again what's happening through that region, and then at equivalence point, what's happening with that in the species and how those concentrations change. And then obviously after equivalence point, if you carry on adding acid, what happens there. So you need to go through those 4 one by one. So for the first part, there's really not too much to say. The initial pH is due to the dissociation of this weak base, which produces hydroxide ions, and because we get a reduction of hydroxide ions, we'd expect it to be slightly basic, the solution, so we'd expect a pH greater than 7. Okay, but obviously this is only a partial dissociation. Now we're going to move on to what happens after that. Now, as we add hydrochloric acid, HCl obviously, when that's put into water, produces hydronium ions and chloride ions, so it's the hydronium ions that are going to be doing the reacting. And what we'll have here is this equation, so you need to write these equations really. This will be the base reacting with the acid, and that's going to produce the conjugate acid and water. Now this is where we describe this as being the buffer region, because as we have the addition of the strong acid, the base is capable of buffering it, so we don't get much in terms of a change of pH. It does change, but not significantly. We do have both species present. Once we start adding H3O+, we get more of the conjugate acid being produced. So we're just going to talk about how basically this reaction proceeds, where we're going to gradually go from having large amounts of the base, of the weak base, and less of it as we add the H3O+. We need to talk about that this is the buffer region, and then we're going to have equal amounts of this around halfway to equivalence point, and then as we carry on, we're going to have more and more of the weak acid present until we get to equivalence point, where we're going to have all of this being present. We're going to have all of the conjugate acid being present once it's been neutralized. Now at equivalence point we have the weak acid present. Remember we started with a weak base. Through that reaction with HCl, by equivalence point it had all turned into the conjugate acid, and so at equivalence point the conjugate acid can dissociate in water and produce a small amount of the conjugate base and a small amount of H3O+. Now this H3O+ means the pH is going to be acidic at equivalence point. It's not going to be equal to 7, so we're going to have a pH that's going to be less than 7 at equivalence point because of this reaction here. Now after equivalence point the pH is really just due to the fact that we carry on adding HCl, and we could in fact work out that pH just based on how much the concentration of the acid was, and then how much it's been diluted by the total volume and how much HCl is present. So at any point you could actually work that out if you had to. So the final one's fairly straightforward. There's no calculation required, and let's move on to part B.